Okay, this is going to be our first video on magnetic fields and magnetic forces. This is going to be chapter 27 from the text. And in this chapter, we're going to be studying how moving charges and currents respond to magnetic fields. We're gonna see how we can calculate these magnetic forces and magnetic torques. We're going to talk about things things like why magnets can pick up iron objects and do a bunch of calculations with these forces and torques and things like that. Okay. So we're going to start off in chapter 27 by looking at section 27.1. That section is titled Magnetism. This is sort of qualitative look at magnetism. There's no calculations in the first section. And for that reason, we're going to kind of look at it, and then I'm going to pair this up in this video with section 27.2, where we start to develop some ideas of how we can calculate magnetic forces. Okay, and there's going to be some equations that we sort of generate and some calculations that we can do. So this video is going to have sections 27.1 and 27.2 in it. Okay, and we'll get started here. So we're going to start off sort of thinking about permanent magnets, okay? And so we know that permanent magnets are gonna exert forces on each other, right? If we bring two permanent magnets together, either they're going to repel or they're going to attract each other. They're also going to exert forces on iron that's not magnetized. And if we take some iron and bring it in contact with some sort of a natural magnet or something that's already magnetized, that metal, say for example we take this iron and it's in the form of a rod. Let's say we bring this iron rod in contact with something that's already magnetic, some sort of a magnet that we've already magnetized. The iron rod will become magnetized, and then if we take this iron rod, we could, let's say it's a very thin rod. Let's say it's like the size of a needle. We could place this thin rod on some sort of a very light floating object floated on water, and this magnetic rod would tend to align itself with the north-south direction of our Earth, right, of our planet. This is like how a compass works. This is actually exactly what a compass is, right? Just a magnet that's free to rotate around a central axis, and it points us in the direction of north and south, right? So before we start talking about the relationship between magnetic interactions and moving charge, we're going to discuss the interactions of permanent magnets in terms of magnetic poles. Okay, so if a bar magnet is free to rotate, its end, as we just talked about, its end is going to align itself with its north pole is going to align itself with the north pole of the Earth, and we call the north pole of the magnet its north pole. Okay, and its south pole will point toward the south direction. Again, assuming that we have a magnet that's like a bar magnet, that's just like a straight line, right? So if we do some experiments with these magnets, as I'm sure all of us have seen over the years, at some point you play with magnets, you'll see that opposite poles will attract each other. Excuse me, and like poles will repel each other, right? As we see in the diagram below here, right? So we have opposite poles attracting, like poles repelling each other, and then either pole will attract non-magnetized iron, for example, right? So we'll have it'll attract the iron nail here, whether we point the south pole or the north pole in its direction. Okay, and so we've all seen these sort of things playing out. We also know, or we've probably heard, that the Earth itself is a magnet with a south magnetic pole pointing in the direction of our north geographic pole. And this is why why the north pole needle of our compass points to geographic north. It's actually because that's magnetic south for our planet, right? So we can kind of see these are our little compasses. They're sitting on the magnetic field lines of the Earth here, and they're always pointing in this northern direction. Okay. We could talk a little bit more about the poles of the Earth and magnets, but that's basically the idea. the we can sort of define the direction of our magnetic field at any point by looking at what a magnet does, right? So we can think about what the direction of a magnetic field is at any point by asking, well, what what force will a north pole at that point experience? What's the direction that the force experienced by a north pole at that point would be? And that is the direction that we call the direction of our magnetic field. So the direction in which a north pole would experience force is the direction of the magnetic field. Okay. So now we want to take a quick look and see some of the differences between magnetic poles and electric charge. Okay. And so one of the main differences, I mean, in the end, the main difference that we're going to be interested in is sort of what's illustrated here in this diagram. So in the case of electric charge, we can have isolated positive and negative charges, right? We can easily just have a positive charge or a negative charge, or some combination of the two, like we might find in an atom. We have our negative electrons zipping around our positive nucleus and so forth, right? But in the case of magnets, there's no way for us to isolate poles. If we take a magnet and we snap it in half, we don't end up with one chunk that is a north magnetic pole and one chunk that's a south magnetic pole. We're just subdividing the magnet. We split the magnet in half. We end up with two magnets, each with a north and a south pole. No matter how small we do this, we're never going to find an isolated north or south magnetic pole. Okay, so this is sort of one of the key sort of things that underpins a lot of our ideas in physics. If we found that there was such a thing as a, what we call them, magnetic monopoles, a single magnetic pole, if we found such a thing in nature, this would change a lot of our ideas about physics. But so far there have been extensive searches, and as far as we know, there's no such thing. So whenever you have a magnet, no matter how small you slice it up, you're always going to end up with slicing it in two, you'll end up with two magnets, not two single poles. Okay. The final discussion from 27.1 here is magnetism and moving charge. Okay. So there's a relationship between magnetism and moving charge that's been known for some time now. And so we're going to look at these ideas more, but we're just sort of introducing them now. So a current carrying wire, if you have a current carrying wire, let's say you're close to some sort of a wire carrying a bunch of current, it's going to deflect the needle of a compass. So clearly it's producing some sort of a magnetic field because it's deflecting the needle of our compass. So our compass is no longer pointing it toward our geographic North Pole. It's kind of pointing in the direction that would be dictated by this moving current. Okay, and if you take a magnet near a conducting loop, which we're going to look at later also, if you take a magnet and you move it rapidly close to a conducting loop, if you have like a loop of wire or something and you move a magnet close to it, you're going to cause some current in that loop. So we're going to look at both of these ideas as the next couple of chapters go on and do some calculations with them. So that should hopefully be sort of bringing us closer to our goal of unifying the ideas of electricity and magnetism. Okay, and that's sort of going to be the goal as we go on. We're going to have this sort of idea that So do I introduce it? Yeah, okay, so hold on. Let me double check my notes here. I want to make sure that I'm not introducing the idea sooner than I want to. Okay, so we're going to talk about it in the beginning of 27.2 here, but basically we're going to have this idea of electric and magnetic interactions being connected to one another. Okay, and as I said, we're going to build this idea up over the next several chapters. We're going to build up this idea of electricity and magnetism, and this is eventually going to culminate in Maxwell's equations if we have time to get to them. But before we do that, we're going to sort of delve deeper into just magnetism on its own, and that's what we're doing here in chapter 27.2. And this is what I wanted to mention before, but we're going to talk about it a little bit more in detail here. So starting with section 27.2, we're going to start talking about magnetic fields, and to do that we're going to sort of remember the way in which we described electric fields, right? So we started off by thinking, well, well, we wanted to come up with a way that we could describe the forces experienced by some particle, say particle B, as a result of particle A, if both of these were charged particles. The way we did this was we set up, so we took a look at charge A. We talked about it creating an electric field in the space around it, right? So we had some charge producing some electric field in the area around it. We then looked at that electric field, and we built an equation for how the electric field, if there's some charge Q sitting in that electric field, what force that charge would feel, right? So the process sort of went, you have a charge distribution, it produces an electric field, then that electric field is what imparts the force onto the second object, right? So in analogy with this idea, we're going to develop the idea of magnetic fields in a very similar way here, okay? So same idea is going to happen here. First, we're going to start off with moving charge or currents, basically the same thing. They're going to set up magnetic fields in the space around them. This is going to be in addition to the electric field that they're going to set up, right? Because they are electric charges, so they're going to have some electric field and some magnetic field. After we have this moving charge setting up its magnetic field, then it's the magnetic field that's going to exert the force on any charge moving or any current close to it, right? So it's the same idea as the electric field, but now it's with moving charges and currents that are setting up these magnetic fields, and moving charge and currents are experiencing the influence of this magnetic field as they move through it. Okay? So for this chapter, we're going to focus on the second part of this idea. We're going to have an already set up magnetic field, and we're going to look at how this magnetic field exerts force on moving charges and currents within it. Okay? So I think I basically say pretty much what I said just here in these notes. Like the electric field, the magnetic field is a vector field, right? So we should probably mention that, right? The magnetic field is also going to be a vector field, just like the electric field was, right? And the direction of the magnetic field is going to be defined as the direction that a north pole on a compass would point, right? Just the same stuff we talked about before. But now we're going to sort of formalize that definition in terms of a formula that we can use to calculate things. Okay, so let's scroll down a little bit and let's build that formula. So this next paragraph really kind of just describes this formula, and really the paragraph is kind of more complicated than the formula is. So I'm going to kind of read through it, but in the end, all that we're trying to say is exactly what we see in this formula. Okay, so we're going to find that magnetic forces on a moving charge, which we denote by F, are going to scale linearly with the magnitude of the charge, so it's going to scale linearly with Q. It's also going to scale linearly with the magnitude of the magnetic field. So we give magnetic field this symbol capital B. That's going to be our magnetic field, just like our electric field was E. The magnetic field is B, and it is a vector field. Okay. The force is also going to scale linearly with the portion of the velocity that's pointing in the direction of the magnetic field. Okay, so it's kind of harder to see here, but easier to see in these versions. And I'm going to talk about each of these equations in a moment here. Okay, we're also going to find that the direction of our force is going to be perpendicular to the plane determined by V and B. So you can imagine, and again, there's going to be some diagrams below where I'm going to go over this, but you can imagine that the vector B and the vector V define a plane, right? If you imagine one vector pointing in three-dimensional space, it kind of defines a single axis, right? It defines a single line that you could draw through all of space. If you then have another line which intersects that first line, i.e. we have two vectors, V and B, the two of them define a plane, right? If you think about it, no matter how you draw these two vectors, you can draw a plane through both of them, right? Assuming that their tails are touching, right? You can draw a plane through both of them, and then we're going to find that F, our force that's experienced by this particle with velocity B traveling through magnetic field B, is going to be perpendicular to this plane. So that's quite a mouthful there, but we're going to see sort of how that all plays out in the diagrams below. This is the formula that we definitely want to have in our minds here. So this is it. Magnetic force on a moving charged particle is going to be, well, it's going to be a vector quantity, and it's going to be equal to the particle's charge times the cross product between the particle's velocity and the magnetic field. Okay, and those are both vector quantities. That's why it's a cross product. Okay. So there are other ways that are useful to write this equation. So we can write this equation stripping off the sort of vector nature of it and just picking off the magnitude of f. We can write it in these following three forms. They're all basically equivalent, but they're kind of nice to think about in different ways for different reasons. So first we can write the magnitude of f is equal to the magnitude of our charged particle, like the magnitude of the charge on the particle, times the portion of V that's perpendicular to B, right? So if we have some fixed uniform magnetic field and our V is changing, it's kind of nice to think about our V changing, and then we're always trying to pick off the part of it that's perpendicular to B, and that's going to give us our F. But we can also think about it in these terms. We can say, well, again, it's going to be equal to the magnitude of our charge times our V now and the portion of B that's perpendicular to V. So it's always about picking one sort of main direction and then looking at something else that maybe is changing, and then we're kind of trying to pick off the part of it that's actually perpendicular to our original direction, right? And we can kind of see these in some examples that we may do later in the chapter. Finally, this third version here, this is sort of our direct translation from the cross product. If we are looking just for the magnitude, F is going to be equal to the magnitude of Q times the magnitude of our velocity times the magnitude of our magnetic field times the sine of the angle between V and B, right? And that's just going to be our phi here, right? And we've probably seen this before. This is just another way to write the magnitude of our cross product down without getting any information about the direction, right? But we always know that our F is going to be pointing perpendicular to both V and B, right? So that's sort of a way that you can get information about the direction of F if we have its magnitude, right? So here we have a bunch of diagrams that are kind of going to just illustrate what we're talking about. These are all good diagrams to sort of get an idea of how these things are going to work out. I'm going to go through each one of them. We also want to note that the figure at the bottom of the page here that's not on the page yet, this figure down at the bottom, is a very nice sort of refresher on how the right-hand rule works. Maybe some of you have seen it before, maybe some of you haven't. I'm going to go through it in some detail here. So the right-hand rule is going to be a tool that allows us to determine the direction in which our F is pointing if we know the direction of V and B. Okay, so let's start going through these diagrams that we have here. So in figure A here, we have charge moving parallel to the magnetic field, right? So we have our V. Well, first we have our Q, we have our V pointing in this direction, and we have our B pointing in this direction. So because V and B are pointing in the same direction, V cross B is going to be equal to 0, right? Or you can also think about it in terms of our sine here. So the sine of 0 degrees is just going to give us no value. So this particle that's moving with a velocity that's parallel to the magnetic field experiences no magnetic forces, okay? And again, same idea if it's moving in the opposite direction, right? This is just the sine of 180 degrees. And again, we're going to pick up no magnitude to our magnetic forces, okay? But if we have a different situation here, let's say we have our magnetic field lined up like we have here, so we have some B vector like this, and this is a positive charge here, and it's moving in this direction, so it's moving in some direction that is not parallel to the magnetic field. Well, then V cross B is going to point upward here in this F direction, okay? And really this diagram C is just the maximum case of diagram B. If it's actually a right angle between our B and V, our sine phi is going to give us 1. That's the maximum value it can give us. And our f is going to have the maximum magnitude. We're going to have a magnitude of f which is equal to QVB, right? And so where are we getting this sort of pointing upward direction from the cross product, right? Like how do we determine that? Well, we determine that using the right-hand rule, which is explained here. Okay, and this is really a sort of important tool that we want to kind of learn and memorize and be able to use pretty easily. So the first thing to remember is it is the right-hand rule. If you use your left hand instead of your right hand, you're going to be off by a minus sign always, right? And we can kind of see why that is. The way that this works is you want to identify where your v vector and your b vector are. If you point your fingers, like make your hand like in a straight line, as though you're sort of almost I don't know, gonna like karate chop the table or something, and you lay it on top of the v vector, and then you curl your fingers. This is your right hand that you're doing this with. You curl your fingers in the direction that B is, right? So let's say you're looking at this diagram here. You place your hand on top of this V vector. You curl your fingers in this direction with your right hand. If you do that, you're going to find that your thumb on your right hand is pointing in the direction of F. Okay, that's always going to be true. So now you can imagine it for this situation. Let's say you have V. You place your hand on top of it. You want to curl your fingers sort of in the inward natural curling direction of fingers. Well, you're going to have to flip your hand over, right? So you're going to have your hand flipped over. Now your fingers can curl in the direction of B, and your thumb points in the direction of F. Okay, that's the right hand rule. If you're dealing with negative charges, same idea. This is just this diagram here. These are just the same diagram, right? If you have the same diagram here, you just do the same thing, hand on V, curl your fingers in the direction of B. Now your thumb points upward, except you're dealing with a negative charge. So you just use the right hand rule and then apply a minus sign, which means instead of pointing upward, it's pointing downward. Same thing here. Your fingers will curl in this direction. Your hand will be on V. Your fingers will curl towards B. And so your thumb is going to be pointing downward. But you have a minus sign here, so instead of the downward direction, you pick the upward direction. Okay, so it always kind of works that way, and this is always going to give us our direction for our force due to the magnetic field on a charge, on a moving charged particle. And so we really want to kind of remember. Well, the key things to remember are how to do this, and that it is the right hand rule. Okay, so we're always going to be able to get this direction. It's always going to be perpendicular to the plane. You can see here, right? The plane that's produced by V and B is the plane in which V and B live, right? This plane is locked in this position because V and B uniquely define a single plane, okay? And F is always going to point perpendicular to that plane. And the question is which direction, up or down, or depending on how you have this thing oriented in one direction or the other, and the right-hand rule is what tells you which direction that is. Now the right-hand rule is just a sort of useful way of remembering what cross products are really telling us, right? And so this is kind of the thing here. We're going to make a decent bit of use of cross products in this chapter. If you're uncomfortable with cross products, or sometimes called vector products, or you don't remember how to use them that well, definitely go back and review your cross products. We're going to need to be able to use them. If you find that you're still confused, you don't remember how to use them, please come and see me. I'm happy to help out. We can talk about cross products whenever you'd like. Okay, so here really this is just the same thing again. We have the right hand rule being used. V cross B, right hand goes here, fingers curl in this way. We have F pointing in this direction because it's a plus sign. Same thing here, except now we have a minus sign, so our thumb would point in this direction, but the minus sign means go in the opposite direction, right? And so we have an F pointing downward here, right? And this is where the minus sign kind of gets worked into the cross product, right here. Positive sign for Q, or no sign meaning positive. Here we have a minus Q, and so we have our force pointing downward. Okay. Last note on Excuse me. Let me actually just pause the video and clear my throat. Sorry about that. So last note here on magnetic field before we move on to the next sort of subsection here. The SI units for magnetic fields they're actually a composite unit. So we end up, if we were to clean up this equation, we would end up seeing that the units of our magnetic field would have to be newtons per amp meter. But we give this conglomeration of units a nice symbol. So 1 Newton per amp meter is 1 Tesla. Okay, so 1 Tesla. A 1 Tesla magnet is actually quite a powerful magnet. We're able to in the lab make slightly more powerful magnets than 1 Tesla. We could make not at our lab here at UFV, but at big labs, you could make I think you can make probably a 20 Tesla magnet, but that kind of gives you an idea of what a powerful magnet would be on the scales of sort of what humans can make. If we talk about electromagnets and we're just pulsing them very quickly, like you would see at certain accelerators or something, you could probably get up over 100 Tesla. But anything higher than that is not something that we can easily make here on the Earth. Now, nature has some much more powerful magnets that we could talk about, but basically 1 Tesla, all of that discussion basically to say that 1 Tesla is a fairly large magnet, right? A fairly powerful magnet, or a fairly powerful magnetic field. Okay, so the next thing we want to talk about is measuring magnetic fields with test charges. There's not a whole lot to say here. Basically, it's just a sort of application of this equation that we have up here, 27.2, which is really going to be one of the key equations for this chapter. So we want to definitely keep that one in mind. But how would we measure a magnetic field if we had a test charge? So one nice way to do that is to just take charged particles with some known velocity and observe them as they fly through the magnetic field. If we do that and we see that the charged particle is being deflected, if its trajectory is changing as it moves through the magnetic field, well, we can do things like calculate what the deflection is, and we can tell a lot of interesting things about the magnetic field from that. So this is kind of what this image is showing us here. What do we have here? We have an old cathode ray tube. Cathode ray tubes are like the things that would make up old computer monitors. You remember, like the big chunky monitors, or old TV sets that aren't flat screens, but are like the old school ones where they used to have the big cathode ray tubes inside. And so basically what a cathode ray tube is it's just accelerating electrons to some known velocity. And because we know the velocity and we know the charge on the electron, if we see that this beam of electrons is being deflected and the trajectory is not a straight line but it starts to curve, well, then we know right away, we can calculate sort of what's going on. We know the velocity, we know the charge on the electron, so we can figure out what B is because we can figure out what F is, right? And so you would need to be a little careful. Oftentimes you're going to have to deal with the force. So the equation that we see here is basically the magnetic force is this part here times Q, and then this first term that we have here, this is electrical forces, right? So these are charged particles, so they're going to often experience magnetic forces and electrical forces at the same time, and it can be a little bit difficult to sort of get to the bottom of which is which, because you're often measuring both at the same time, and you're going to end up seeing an F that kind of looks like this, right? So this is also a useful equation. We want to remember that these are charged particles. There could be contributions from both magnetic and electric interactions sort of playing a role in the force that they're experiencing. Okay, so to wrap up this video, we're going to take a look at 2 examples, one from the textbook and one extra one that I have. I just added in an extra one because I didn't like that they kind of didn't even address the idea of cross products. It's very important that we can do cross products. So I have one that has a very, very simple cross product in it, just to remind us of how cross products work, and we'll do those 2 examples sort of now. Okay. So this first one, like I mentioned, is from the textbook. This is 27.1. This is magnetic force on a proton. So we have a positively charged particle. We have a beam of protons. Protons have a charge Q equals 1.6 times 10 to the negative 19 coulombs. It's moving at 3 times 10 to the 5 meters per second through a through a 2 Tesla uniform magnetic field directed along the z-axis. So we see it here. This is our magnetic field directed along the z-axis. And so the velocity for each proton lies in the xz plane and is directed 30 degrees to the positive z-axis. Okay, so basically we're like turning this. Yeah, you can see they've labeled it 30 degrees here. We want to calculate the force on the proton, right? So this one's extremely simple, just like the one that I have set up for us here. Obviously, these can get more difficult, and we'll look at more stuff as the chapter goes on. But we're going to start off with just this. What we want to use here is one of the versions from the boxed equation under the main equation that we have here. We're going to make use of this last equation here. Okay. So we want to calculate the magnitude of the force. And so the magnitude of the force is simply going to be equal to the magnitude of our charge. It's positive, so I won't bother with the absolute value symbols. The magnitude of our velocity, the magnitude of the magnetic field, and the sine of the angle between them. Okay, and really it's just that simple. We just plug in the numbers, and so it's going to be 1.6 times 10 to the minus 19 coulombs times 3 times 10 to the 5 meters per second times 2 Teslas times sine of 30 degrees, right? 30 degrees is the angle between from V to B, right? If we do that calculation, I won't do sort of simplify it any further. We'll just go in one step here. If we do that calculation, we're going to find 4.8 times 10 to the minus 14 newtons is the force experienced. And could we find the direction of this? We could easily find the direction of this, right? We would just use the right-hand rule, place our right hand on V. If we want to be able to curl our fingers in the direction of B, well, our thumb better point downward, right? So we're going to put our hand on top of V. It's going to curl in the direction of B. Our thumb points downward, so this F is actually going to point downward. Like, we can't quite see it here, but I guess in the negative j hat direction, right, in the negative y direction. And so that would be the pointing of our force vector. So I guess we could write this like F equals 4.8 times 10 to the minus 14 negative j hat newtons, right? And so that's basically it, right? If this was a negative charge, we would have done the same thing, except that we would add an extra minus sign, and so our negative j hat would become positive j hat. But it's positive, so in this case, this is our answer. Or really, they only asked us for this, so this is our answer here. Okay, and then I added in another one that's going to kind of make us have to do a little bit of a cross product here, but a very simple one. We won't have to break out any complicated tools here. We have an electron, so this is the magnetic force on an electron, basically the same setup from above. We have a slightly different velocity, and we have a slightly different magnetic field. They're basically, are they pointing in the same directions? They're not, right? Because we had, our V didn't point in the I hat direction. Okay, so what do we have here? We're going to just simply use the main equation that we have for force. Our force is going to be equal to, or our force as a vector is going to be equal to Q V cross B. And we can simply substitute in numbers from here. We have our Q, so this is going to be minus 1.602 times 10 to the minus 19, negative, right? And then we're going to have this cross product. So I'm going to pull out the magnitudes of both of these and then just do the cross product of the unit vectors, right? So we can pull out the magnitude of V. That's going to be 3,000. That's meters per second. I'm going to pull out the magnitude of B. That's 0.5. And then we're left over with this cross product. Our V points in the I hat direction, cross our B that points in the J hat direction. So we need to know what I cross J is. Okay, and if you think back to your earlier work, to when you've looked at cross products in 111, you should remember that I cross J is just K, right? So I hat cross J hat is K hat, and so we get our answer. If we plug through these numbers, we're going to find that F is equal to minus 2.4 times 10 to the minus 16 k hat newtons. Okay, does that kind of make sense with I'm not sure why I didn't include the newtons there. Does that make sense if we sort of think about the right hand rule? Well, it kind of does. If you line if you're dealing with a right-handed coordinate system, right? Let's say you have a coordinate system that you have. Let's say this is your I hat, okay, and you have your j hat pointing into the page, right? I'll take this to mean pointing into the page. So this is like I hat, j hat. If you have a right-handed coordinate system, this is going to be your k hat. And if you take your fingers, line them up, well, the fingers of your right hand, line them up with I hat, like lay your hand flat on the page or the monitor or whatever, and then curl your fingers into the page so you're going toward j hat. Well, your thumb does point in the k hat direction, and that is exactly what we find here. Now, will this actually point in the k hat direction? Well, no. It has a minus sign, right? So it's actually going to be a force pointing down in this direction. But whether we have a minus sign here or here doesn't really matter. In the end, we know that this thing is going to point with this magnitude in the negative k hat direction because we pick up this minus sign, and that shouldn't be surprising because our charge is negative as well. Okay. Okay, so we'll leave this video here, and we'll pick it up with 27.3 in the next one.